Hi, good afternoon. My name's Jan Gray. I'm a consultant. I live up in Bellevue, Washington. I'm going to be telling you today about the GRVI Phalanx FPGA accelerator framework that I've been building that employs RISC-V soft processors. So FPGA accelerators are getting pretty hot. I was at Supercomputing last month, and there were quite a few new startups and companies very interested in FPGA accelerators for HPC and, of course, in data centers. I consulted on Microsoft Research's Catapult project, which you may have seen had a paper in ISCA about doubling the throughput of a Xeon data center on a workload which was Bing search ranking. Earlier this month, Intel completed their acquisition of Altera for $17 billion. And so there's considerable industry interest in complementing regular processors with FPGA acceleration. So why is this so? Well, FPGAs are interesting computing devices. They have enormous parallelism, both in the lookup tables and especially in the memory bandwidth to the many block RAMs on the devices. You can, of course, specialize the data paths to your particular application or data shape. And FPGAs are, compared to other devices, much better connected. So you can directly connect them to 25 gig or 100 gig Ethernet networks, PCI Express, many channels of DRAM. And future FPGAs will have high bandwidth DRAM in the package and so on. So very high bandwidth interconnect. And so with that, you can build systems with either very high throughput in aggregate, all the parallel accelerators, or achieve very low latency for messaging applications over an Ethernet, or low energy compared to GPUs or CPUs. So this is all great, except for two obvious challenges. The first is software. How do I take my C++ workload that's being changed every day by my C++ developers and somehow get it running on the hardware? Well, there's been a bunch of approaches with RTL and with high-level synthesis, but I think the breakthrough in that area is OpenCL. So if your workload is expressible as an OpenCL kernel parallel invocation, then there's some nice tools coming from Xilinx and Altera that maps that into a fixed, very deeply pipelined data path. But it's not clear that OpenCL will handle all parallel programming models, shapes of applications. And mapping the application into a fixed function data path means that if you change your application or the programmer has a better idea, you then have to spin a new FPGA, which takes several hours. Another problem you have is the physical implementation of the hardware. So you're building this FPGA accelerator. It's got a couple of 25 gig or 100 gig ports on it, lots of memory channels, hundreds of accelerators. And somehow you have to carry all these 100 gigabit per second data streams across the device and allow all the accelerators to talk to each other and to the very many I/O devices that you have. So getting time enclosure, just getting the thing to physically work is tricky. So what I'm working on is an approach where we use, somehow we solve these two problems. We get your application running on the FPGA quickly because it's a mostly software stack that we're using, and that we're going to have a way to connect all these accelerators and I/Os together. The general approach is to make clusters of processors and accelerators, and then connect them all up on a high-efficiency NoC, network on a chip. Now, to get acceleration, that is to be competitive with x86s and ARM cores and ASICs, means that every component of the system has to be very highly tuned and very efficient. So in terms of the processor cores, we're going to need a very efficient processor core. And because we want the software guys to use their familiar open source software, it needs to have an open source infrastructure, including GCC and LLVM and glib and Linux ports and so on. And fortunately, that's where RISC-V comes in. It gives the processor developer a chance to go and build a processor and not have to invest 100 man-years in building all this software infrastructure. The question is, can you build a really FPGA-efficient soft processor? So in terms of my general philosophy to building processing element soft processors, it's to make them as small and simple as austere as possible. Leave everything out of the processor that you can besides fetching instructions, register file, ALU, memory ports. Cut all of that stuff out of the processor so that you can have a very, very small processor. And each of those can go and hit one of these many block RAMs on the FPGA and get as much memory parallelism out of the FPGA as you might have. And that means that some function units, for example, a barrel shifter or a multiplier, might get taken out of the core and put into the cluster and shared amongst a set of cores. And there's no substitution for sweating every single LUT that comes into that processor core, because you're going to create a lot of them. So if you use this general philosophy, you'll get a core that looks a bit like this. So this is the floor plan of a RV32I data path. It's about 250 LUTs. The red column there is two 32 by 32 register files. The orange and yellow stuff are the first and second operand multiplexers, result forwarding, and registers. The green column is the ALU. The blue column is a result mux. There's some other logic around for the program counter, the comparator for set less than, and branches, and so on. And that's about it. It's about 250 LUTs if you really technology map every part of the data path very, very carefully. Then you add a control unit to that, and you get about a 300-ish LUT core. It depends what options you turn on. So I'm calling this core GRVI, the Gray Research RISC-V core. Its purpose, again, is as an efficient parallel processing element. I'm not trying to build a general purpose RISC-V core that runs any embedded software stack. It's just to be a thing that runs a small C++ compute kernel. The core is a 2 to 3 stage pipeline. It runs at about 300 to 400 megahertz, depending on the pipeline depth and where you put the block RAMs on the device, and so on. And so at 300 MIPS and 300 LUTs, it gets about 1 MIPS per LUT. And it's a very interesting figure of merit. If you start thinking about spending FPGA resources on anything else, you should say, well, if that costs 10 LUTs, is it worth spending 10 million instructions per second on that hardware structure? It really clarifies your decisions. So here is that core implemented in what's a small to mid-sized modern FPGA, Xilinx Kintex UltraScale 40. It's down in the bottom right corner there. The overall device has 240,000 LUTs and 600 block RAMs. So the question is, how many of these processors can you put on a device, and can you do something useful with that? So what is the kind of memory hierarchy, and what kind of structure would you use to compose these into a useful system? Well, at the first level of a hierarchical parallel computer, these ultra-scale FPGAs, again, have about 400 LUTs for each block RAM, which is roughly one processor plus some overhead per block RAM. So how do you tile that down? Well, one observation is that you can share one block RAM, which has 2 ports, to form 2 instruction ports. So you can put one copy of a kernel and have it serve up 2 processors. Then you should take a number of block RAMs and pool them together and make that into a shared data memory for the cluster. Really, the question is, what's the minimum size cluster memory that will hold your application's critical working set of memory? So for this, I've arbitrarily chosen a 32K cluster memory, which means you have 8 block RAMs, which means you can have 0 to 8 processors in that cluster before you run out of room for processors. So in the example that I'm going to be working through here, it's that green one where I've spent 12 block RAMs for 8 processors and 32K of cluster memory. When you floor plan the cores as well, you get a cluster tile that looks a bit like this. There's 8 cores, there's 12 block RAMs, and there's some interconnect that I'll explain on the next slide. So here is the cluster topology. As I said, you have this column of 8 processors that share 4 copies of a compute kernel. Then they have a multi-stage, there's a 2-to-1 concentrators and a 4x4 crossbar to access into the cluster data memory. That uses the block RAM's many ports to build a 4-way address interleaved store there, so you can support 4 concurrent reads or writes per cycle from the 8 cores. And on the other side of the memory, there's 8 32-bit ports, which you can use to hook up to an accelerator. So the aggregate bandwidth on the right is you can do 8 interleaved reads, or you can do 1 256-bit per cycle read or write between the accelerator and the cluster data RAM. So the programming model here there's no caches. You put a small kernel into the processors. All the cores can see the same 32K of shared memory. So you're going to need programming models that work well in that kind of clustered environment. Some do, some don't. Oh, and of course, the processors can collaborate with the accelerator. The processors can do the irregular computation that sets up the work, and then the accelerator can go and fetch lots of data per cycle and do lots of computation. So at the next level of the hierarchy, okay, I've got this 8 processor cluster that uses 12 block RAMs. I told you the device has 600 block RAMs, so potentially we could have 50 clusters of these on one device. How are we going to interconnect that? Well, you could go and use a 5-port virtual channel router, and the problem is that when you implement each of these things, each of these subcomponents, which is reasonable in an ASIC, it's not very efficient in an FPGA. So the buffers that are used as the virtual channel implementation mechanism use up a lot of FPGA area. The logic to control all that uses a lot of FPGA area. The best tuned work on this, like the MIT Connect work, spends about 1,500 LUTs to build one 32-bit wide 2 or 4 virtual channel router. And so that's like the area of 5 processors to build one router. That's not a great trade-off. So I don't advocate this approach for doing this in an accelerator. Instead, a few years back, I kind of rethought how you build NOC routers on an FPGA. And the approach I took was to just focus on moving the bits. So no segmentation and reassembly, no flits, no buffering, no virtual channels, no credits. Throw out all that orthodox stuff and just focus on what's the data path of moving bits quickly from place to place on the FPGA. So you end up with an extremely simple data path, particularly if you go from a 5x5 switch to like 3x3 or a 3x2 switch. And so it's very simple. It maps beautifully into the FPGA LUTs. It's so small that you can then have very, very wide channels, as I'll demonstrate. And it ends up with a very, very short transition from one router to another, as you'll see. When you take the area delay product of a conventional VC router implemented in FPGA and you compare it to this is about 1/100th of the area times delay, which is transformative. So here's the idea of what this directional 2D torus looks like. Any router is on an X ring and a Y ring. So the client ingress comes into a router. It generally uses dimension order routing, so it goes in the X coordinate to the right XY location, and then it transitions to the Y coordinate, goes down some Y ring, and then comes out at a client. This expression of it here has just 3 inputs and 2 outputs. So I even get rid of the output channel to the client to make the router switch simpler. Now, routing on this is deflecting. So there's no buffering. So what happens when there's a message from the X input and the Y input, and they both want to go out the Y output? The X input will deflect all the way around the ring. So if you have an if the network is heavily loaded, it bogs down. But as long as the traffic on the network is at a light injection rate of about 10 to 20%, depends on the size of the network will efficiently deliver all the traffic. So when you implement that in an FPGA and you use the same philosophy of carefully technology mapping and carefully floor planning the router, you can build enormously large routers and have them span the whole chip. So this is an example of just routers with a dummy client. Each of these rectangular regions here is a 256-bit wide router. And you can pipeline this, each router stage is one pipeline stage. And in this case, it's not folded, so you can see some registers for the long path back across the whole die. But this example here runs at 400 megahertz, carries 256 bits per clock per link, so it's about 100 gigabits per second in these channels, and it uses less than 5% of the FPGA area. And that means that you can now, instead of your problem of trying to fit your big SoC is not, how do I put all my accelerators near all the DRAM ports? You can put them anywhere on the die. They just have to get on at some router. Their data will be carried to the DRAM port at full bandwidth, or the results will be back from the DRAM port at full bandwidth. So this router ends up with kind of optimal area and delay. You can't use fewer LUTs and light up all those output channels. And you can't use fewer LUTs and do a switch because it's a 1 LUT deep data path. And I think that this router will change the way that people design large SoCs and FPGAs, because basically anything can be connected, and where you put stuff on the die doesn't matter very much. So when you attach that to the cluster, we end up with a 300-bit wide router links, which carries a 256-bit data payload, 32 bits of address, and some other control and addressing on the NOC. So the model here now is that processors can prepare 32-byte messages in the cluster data RAM and then do a special I/O space store that causes a 32-byte message to be sent onto the network. Or a 32-byte message from somewhere else might come from the network and be retired in the cluster data RAM. And similarly, the accelerator can send 32 bytes per cycle onto the network or receive 32 bits per cycle. So it affords very high bandwidth interconnection amongst all the memories and cores on the device. So then when you tile that onto the FPGA, and again, you take care about technology mapping and floor planning, you can build this system which puts 400 of these RISC-V processing elements onto the Kintex UltraScale 40, using all the BRAMs and about 3/4 of the LUTs. Of course, there's no accelerators in this implementation, and if you had substantial accelerators in the clusters, you'd probably depopulate the clusters with processors. You might have 2 processors instead of 8 or something. This dive plot shows which sites in each of the clusters is implementing bits of the router. So in this case, I haven't floor planned the router. I've just said use the empty space in each of these cluster tiles to implement the router LUTs. The amortized cost of the router per processor here is just 40 LUTs, and the overall cost on the chip is about 6% of the available LUTs. I'll talk about the status in a minute, but when you power the system on and all the processors wake up and they all send messages to the main processor saying, here I am, send me work on my channel here, and then they go into a spin loop waiting for work, this is what the power looks like. It's about 12 watts. So it's about 250 milliwatts for each cluster and about 30 milliwatts per core total. Now, that will go up when the cores start actually doing work, when I wire up the multipliers, and it will come down when I tune, putting the block RAMs to sleep when they're not being used and so forth. But it's an interesting number. It's not 80 watts. It's just 12 watts. So this is a system with 400 RISC-Vs on a die. It has a 1.6 megabytes of SRAM. That's the whole memory system in this instance. The total not to exceed peak MIPS, if you multiply the processors times the 300 MIPS or 275 MIPS or whatever, is under 100,000 MIPS. And the total memory bandwidth from the processors hitting the cluster RAMs and the accelerator or the network hitting the cluster RAMs is 600 gigabytes per second. So we're really taking good advantage of all those block RAMs. And it's a network that will send or receive from each cluster 32 bytes each cycle until the NOC saturates. So don't pick workloads that doesn't happen. There's also a multicast facility in Hoplite that I haven't turned on yet in the design. And that will let us do things like load a new kernel into all the IRAMs in the device in 3 microseconds by broadcasting the 1,000 words of the kernel to all those IRAMs in parallel. Or you can have a workload, a packet processor, where packets are coming in at 100 gigabits per second, and they get blasted to every cluster, which can then do some packet filtering or whatever on them. At the other extreme, because the cores are so small, you can also build this into a very, very inexpensive, cheap FPGA. One of Xilinx's smallest FPGAs is this Arctic 735T that's in the Digilent Arty system. If you go to DigiKey, it's about $35 quantity 1. I'm sure it's much cheaper in volume. And here's a system with 32 RISC-Vs and a 2x2 Torus. Even in this system, with the slower clock frequency of the Arctic's fabric, it does 40 gigabits per second between clusters. This stuff is all aspirational. This is where I want to take this. I think that this general architecture is a nice building block for building accelerators. You can take a variety of different software parallel programming models and map it onto this. So certainly OpenCL kernels should work well where you take a workgroup kind of cluster, you put a workgroup in a cluster. Or you can do a kind of a Gatling gun packet processing where the first packet comes in and you send it to cluster 0, and the next packet comes in and you send it to cluster 1. And now you have 50 inter-packet time intervals for each cluster to work on its packet. You can, of course, have MIMD programming models if you have more of your block RAM spent on instruction memories. You can have multiple different code bases running in a cluster. You can compose clusters together with messaging, so you can have streams that flow from one cluster to another, each of which does some processing on the stream. And because this is in an FPGA, you can accelerate the whole thing. So you can take the soft processors and add special function units to them. You can have dedicated standalone accelerators that are coupled to the processors or to the cluster memory. Or you can have an accelerator that is itself the client of the NOC. So what's the status of this? The thing booted with 400 processors on Christmas Eve, so it's just coming up. I'm building this week was spent trying to get the debugging and monitor so I could at least send code to all the different IRAMs on the NOC and so forth. So it's crawl, walk, run. So the next thing is to add debugging and tracing over the NOC. And then I need to wrap the Hoplite routers with AXI4 and AXI4 stream bridges that I can start using the AXI4 IP that is in the Xilinx toolkit, and that will let me start using external DRAM, Ethernet, and so on. Porting this back to Altera will be interesting. I'm excited to light up the processor cores on the ARIA 10, which has hard floating point unit DSP blocks. So we should be able to get a great deal, like teraflop of DSP out of that thing. Which leads to the question of what kind of OpenCL stack would you run on this? I don't know yet. And at some point, figure out how to bridge it into the Chisel RISC-V infrastructure. So in summary, I'm using the RISC-V core to not have to worry at all about, a RISC-V ISA to not have to deal at all with the compiler and tools chain stuff that I've had to do in the past. And the resulting system is all programmable in Xilinx's marketing spin, which is hundreds of processors that can run arbitrary software. You can wire it up to accelerators. You can wire it up to high bandwidth I/O. And hopefully, it'll run a variety of different parallel programming models, all connected with a pretty beefy NOC. So thank you very much. Any questions?
Hi, Jan. This is Tommy. So how do we get this?
It's a great question. First of all, it's still coming up. So I have one collaborator. It's actually interesting to develop hardware with a collaborator in another city. You just check it into GitHub, and he syncs it, and now he's got this. Honestly, I'm not sure yet. Obviously, this has some commercial utility, so I have to look into how I should license it. It's certainly my intention that it's available for academic research purposes, but I haven't got there yet. I'd be delighted to talk to people about how they'd like to use it and how they might like to license it. Sorry, I don't have a better answer than that right now.
Dan Wilkerson, independent contractor. So I have a couple questions about your Hoplite NOC there.
Yeah.
So I studied that kind of routing in grad school in the 90s. You make it sound like you originally invented this kind of routing. No citations.
Oh, so I'm not claiming that I've invented deflection routing or bufferless routing. I do, what do I want to say here? I think I took a fresh look at how you build NOCs and FPGAs.
Sure, okay.
The refereed literature on NOCs and FPGAs wasn't going anywhere around this space, and I think it's really a much better way to wire stuff up. Now, let me elaborate for a minute. Virtual channel routers have reasons that they exist, right? You have multiple channels of traffic that you need to carry, but if the NOC is cheap enough, you can just instantiate multiple NOCs. There's no reason to not use a data shoveling NOC of 256 bits and several other non-virtual channel NOCs to carry control traffic or other categories of traffic, and it ends up being cheaper than a virtual channel.
I believe you certain algorithms fit the FPGAs much better. Are you doing no buffering at all? So you're effectively doing what people used to call lockdown routing, where you have to lock down the whole path?
No.
No. So you're effectively doing wormhole routing where you don't buffer, no?
There's no segmentation and reassembly. So a packet, so a message enters the NOC in one clock cycle, and each clock cycle it goes to a different router until it leaves the NOC.
So the entire packet can buffer within a single router?
The clients of the router only inject an atomic message per cycle.
But can an entire message fit in one router?
One beat.
So it's really packet routing then that makes it work well.
So let's give you an example. If you're trying to bring Ethernet traffic over the chip with this approach. And an Ethernet packet is going to be 64 bytes to a really long size. Obviously, you're not going to have a 1,000-bit, or sorry, a 10,000-bit channel. So the clients of the network will segment their traffic into atomic messages. And they'll, if that happens, if they did take a stream of data and they did that, then their client's going to have to reassemble it. But there'll be lots of categories of traffic where you just get on the network and atomically it bops around, and in 10 cycles it's out of the network again, anywhere on the chip.
Yeah, so that's basically packet routing then. You're getting the entire message to buffer every time it has to stop.
Well, there is a buffer. It's the flip-flop. That's the egress port of the router, but it's not conventional buffering. There's nothing elastic about it.
John Vincent from Huawei. Just going back to your power presentation, that was just the system starting up or in its idle state, correct?
This is the idle state, yes.
So if I
in idle state, 400 cores are running in a loop where they're fetching the jump to self instruction. And actually, I guess they're a different loop. They're loading memory from the block RAM saying, has someone sent me a message? And no, and then they go. It's about probably a 5-cycle loop. Okay. So the program counter's incrementing, the memories are getting hit, but it's still, a reasonable amount of power.
Yeah. So if I look at Farzad's power pyramid from before, and
yes.
Have you looked at sort of optimal sizing of your cluster versus the number of clusters? Because there's going to be a trade-off, right? As your smaller clusters and you map a workload, you're going to move a lot more data across clusters versus keeping it local to a cluster.
Yeah,
so,
I haven't looked at any of that.
Okay.
I'm just aware that, the cluster generator is parametric on how many cores and how many block RAMs and how many multiplexers at each stage and that kind of stuff, but I haven't.
Okay, and I guess.
Really what you want to do is have the workload that you care about and then size the parameters for that.
I guess that was my question. You haven't had that done. You haven't got to that analysis yet.
No.
Okay.
Any other questions?
Craig Steele, Totline LLC. I was wondering, in your global message passing communications model, at this time, do you have any kind of synchronization or notification mechanisms, interrupt any hardware?
No.
It's just polling memory at this time.
Again, in the crawl, walk, run, can I get this thing to boot and so on? So right now, the messages can only be sent. There isn't even a remote read in the network. That'll come, but so I have experience with a message passing programming model called Thoth. It came out of Waterloo, and then there was the vkernel system David Cheriton did at Stanford. And that actually works really well here at this very early stage of the hardware. It's a synchronous model where and an asymmetric model where a client sends a message in blocks waiting for a reply. An administrator can receive messages from a lot of clients and then reply to them to unblock them. And in that model, it actually works. It maps perfectly onto the single message send primitive that I've done now. So in the short term, I'm going to build an interesting and useful locally distributed system using that message primitive, and then I'll move on to other things once the rest of the system is really brought up properly.
I'm Trivikram from Google. I want to go back to your Hoplite knock
Yes,
routing. Maybe I don't understand deflection well enough, but can't you have a case where all four, or are these unidirectional links?
It's unidirectional links. Maybe that doesn't show. Yeah, it does. So at a router, there's an X and a Y input, an X and a Y output, and a client input. That's it. And so and there's in the default configuration of the routing function, there's a static allocation of ports according to which inputs are valid. So the second dimension, the Y traffic, has priority. So if there's a valid Y input message, it's routed to the output flip-flops for Y. If there's a valid X message, it goes out on Y if it's not allocated. Otherwise, it goes out on X and deflects around. And only then does the client get a chance to ingress the network. And if the output port the client wants is free, then the network accepts the message from the client on that cycle. Otherwise, the client has to idle, and it can represent that message or another message in the next cycle for ingress. And so there's no buffering anywhere in the network, and depending on how you design the client, there's no buffering in the client either. So in this very, very austere system that I've built here, if the network isn't accepting your messages, then, so let's say that the network's very busy, so it's not accepting this message that this processor is trying to send. That instruction doesn't retire until it does.
Okay.
So buffering would be great and would add some performance, but the area that it would add would reduce the overall machine's performance, and that's why there isn't any.
Okay, we'll have one final question here, and we'll give it to Dave.
Hi, Dave Patterson, Berkeley. So how do you think, given the trends that are going on in FPGAs, how does your architecture, will things get better for your architecture or things get worse?
I think that, what are the trends? The trends are, first, we're going to get maybe 2 more technology nodes that we have visibility to, and we're going to get a doubling of LUTs, doubling of block RAMs with each generation. So that's going to go fine, because the network will scale as square root of n, for example. All the different ridiculous core count parallel machines I've built in the past have all been kind of pointless because there was no memory bandwidth to light up that many cores. So one of the things we're seeing is increasing high data rates on the network interface ports. And finally, Altera has announced, or I guess Intel has announced, that they will have some devices in the next generation that will have high bandwidth memory dies in the package. And so that will take us from having a couple of 10 gigabyte per second memory channels to a couple of 100 to 200 gigabyte per second devices that will actually, looks like it will come in on, I'm guessing that it will come in on 8 channels of 10 or 20 gigabytes. So in that world, you desperately need a NOC so that any agent on any accelerator on the die can talk to DRAM channel 1, DRAM channel 7, network port 2. There's just no way to physically co-locate the accelerators besides all the ports that they might need to access. So I don't know if this clustered decomposition is the right thing for the future, but a NOC is going to be an essential way to build large FPGA systems in the future, I think.
Great. Thanks, John.
Okay. Thank you.